So this video will be our introduction to symmetry, so symmetry and group theory. So if you want to follow along with some of the reading, you'll want to look at chapter 3 of your textbook. Symmetry is often used to describe the balance and proportion in objects or works of art. Used in this context, symmetry is a qualitative and subjective concept. We will use symmetry to better understand the geometry and bonding in molecules using a more objective and quantitative approach. So hopefully by just looking at some of these example pictures that I put up for you, such as the plant or the architecture or the rug here, you can see how symmetry is used to create balance, and you have these repeating patterns. We also have this sense of balance and repeating patterns also seen in chemistry as well. Now, studying the symmetry of molecules will help us to understand how parts of the molecule are equivalent, and this will help us to interpret NMR spectra. The symmetry allows us to determine the movement and vibrations of bonds, including the number of vibrations, and this is relevant to IR and Raman spectroscopy. In addition, the symmetry will help us to create subgroups of equivalent atoms in a molecule. This will aid us in building molecular orbital diagrams, as well as determining what orbitals can overlap to form bonds. So I want to look at some of the objectives we should have for symmetry. First of all, we need to be able to understand some of the definitions. For example, being able to distinguish between a proper and improper rotation, the difference between an identical and equivalent configuration, and the difference between an operation and an element. We also want you to understand the symbols for symmetry operations. What does a symbol mean and how it would move the object, and which symmetry symbols are equivalent. We also want you to be able to determine the point group of an object or molecule, identify all the symmetry elements of a molecule, determine the reducible representation for a given set of objects, determine the irreducible representations that are contained within the reducible representation, also to be able to fill in the characters of a character table for an irreducible representation. And then using symmetry, you should be able to determine whether a molecule is polar or nonpolar. And also using symmetry, we will be able to determine whether a molecule is chiral or achiral. And with the applications of symmetry, we should be able to distinguish between IR and Raman active bands. Lastly, we want to be able to also construct a molecular orbital diagram of a molecule containing more than 2 atoms. Now, some of these things you may not understand what they are just quite yet, so reducible and irreducible representations, we will cover that in one of our lectures. But let's start on the symmetry vocabulary. First of all, the configuration. That's the exact position or orientation in 3-dimensional space of an object. So at the right here, I have a blue triangle. And I just put numbers out to the sides of the corners, just so that gives me an idea of some orientation of where each of the corners on the triangle are. Now, an identical configuration results from an operation returning an object to its original position. So let's say I started off with a blue triangle like this with a 1, 2, and 3. I do something to the triangle, and when I finish with moving that triangle around and I look to see where it ends up, it looks exactly the same as it did before. And the corner that was labeled 1 is still at the top, the corner that was labeled 2 is still at the bottom right, and the corner that was labeled 3 is still at the bottom left. But let's say we have an equivalent configuration. This is an orientation that is indistinguishable from the initial orientation. So again, I start off with the same blue triangle with a 1, 2, and 3. I do something to the triangle, so maybe I rotate it to the right. And when I finish rotating it, the triangle looks the same, but the numbers out here to the sides let me know that the corner that was at the top is now at the bottom right, the one that's at the bottom right is now at the left, and the left is now at the top. So if the numbers were not here, we wouldn't be able to tell that anything was done, but the numbers are just letting us know where the corners move to. So this is an equivalent configuration. Now, a symmetry operation, and it may be real or abstract. is an application to a geometrical structure, and it yields an orientation that is indistinguishable from the initial orientation. So a symmetry operation is something that you do to an object to create either identical or equivalent configuration. Now these symmetry elements, those are the geometrical elements that are used to perform the symmetry operation. So let's say you rotate something, so a rotation would be an operation, but you have to rotate about a line or an axis, and that axis or that line would be the symmetry element. So here we're just going to look at some of the types of symmetry elements, their symbols, and their operation. So the first one we want to look at is the identity, or the whole of space, and its symbol is capital E. And basically this operation is to do nothing to it. A mirror plane, so that's our operation, so that is a plane, and remember a plane is defined by either a line and a point or 3 points. And the symbol for a mirror plane is a sigma. And when you use a mirror plane, you are doing a reflection, so you reflect through the mirror plane. Now our next element is a proper rotation axis. So this is a line, and the symbol for it is Cn raised to the m. And this is what we call a proper rotation. So you rotate something. Now the n here tells me about what fraction of a circle to rotate. So let's say this says C2. So that C2 means that I need to rotate by half of a circle. So that's by 180 degrees. Now, if I don't have anything written up here, there's an understood 1. And then M tells me how many times to do the operation. So how many times to repeat the operation. So if no M value is given, you can assume 1. So let's say I have a C3, 2. The C3 means I rotate it by 120 degrees, or a third of the way around. And the 2 means I do it twice, so I rotate it by 120 degrees, and then again by another 120 degrees. Now our next symmetry element is an improper rotation axis, and this is a line as well. So the improper rotation uses an S compared to the C. And the N still tells you what fraction of the circle to rotate, and the M tells you how many times to do the operation. And we will look again later on in another slide what an improper rotation actually is. Now the last symmetry element that we're going to use is a inversion center, and this is a point. So the symbol for the inversion center is a lowercase I, and the operation is to invert. And another way to define this inversion is an S2. So this inversion is actually a special case of the S2 improper rotation axis. So let's go through and look more closely at some of these operations. We're going to start off with the identity. And remember, the identity is abbreviated E, and it's the operation associated with doing nothing. So all objects possess the identity element. So if the operation is to do nothing, why bother having the identity element? Well, this is the group theory equivalent of 0. So even though we count things, and we start off by counting 1, 2, 3, and 4, sometimes we need to represent that we have nothing. So we use the 0. So this is our equivalent of 0 in group theory. So the identity. So if I look at this benzene molecule, I do nothing to the benzene molecule by the E operation, and it looks exactly the same, and it produces an identical configuration. Now I also have this picture of Franken-Kitty. So this is Penelope for those of you that have been to our Halloween party for the chemistry club. So if I take this picture of Franken-Kitty and I do the identity operation to it, so I do nothing to it, the picture looks exactly the same, and the photo is unchanged. It looks exactly the same. So moving on to the proper rotation. So remember we said that it's abbreviated with a C, and the N tells us by what fraction, and the M tells us how many times to do that operation. So a C2, if we're looking at this water molecule, we rotate it through this axis 180 degrees. So this point that was at the back, this hydrogen atom that was in the back, now moves to the front. So here we have an object that has a C3 rotation axis. So if I do the C3 and I rotate this molecule, so I'm rotating by 120 degrees, the point that was at the top has now moved to the bottom right. So I'm just putting the asterisk just to kind of show you where it moved. Now if we do the C3 operation again, that atom here now moves to this side, so we distinguish it with an asterisk. And if I do the C3 operation again, we return to our original configuration, or that identical configuration that from where we started from over here. Now with some of these C3 operations, we can rename some of these. So remember, this is a C3-2. So this is where we did a C3 operation twice to get to here. And a C3-3 is equivalent to the identity operation, because the C3-3, even though we rotate it 3 times, it looks exactly the same. So it produces the same identical configuration. So we say that those operations are equivalent, and we don't bother listing the C3-3. We just list it as the identity. Now when necessary, the C2 axes perpendicular to the principal axis in a D group are designated with primes. So when we start looking at molecules and we identify the principal rotation axis, it's the axis with the highest N value for the proper rotation axis. So with this molecule here, this has a D4H symmetry. So it has a C4 in the center here. So this C4 is coming out of the plane of the computer. So it's coming out at you. And notice that I can rotate this atom to the right and it would look exactly the same. So that C4, you're rotating by 1/4 of the way through the circle, so you're rotating it by 90 degrees. But we also have C2 axes. So if I have a C2 in the plane here, so in the plane of the computer, I can flip it along this line. So the atom at the top goes to the bottom, and that goes to the bottom, goes to the top, and those that are on the axes stay on the axes. So the C2 that goes through the plane of the atoms, we designate with a C2 prime. The C2 that goes in between the atoms, so there's another C2 that passes along this red line, so the axis here, but rotate around that axis, this atom moves to here, and this atom moves to here, and then these atoms also switch place as we rotate about that C2 here. So the C2 that passes in between the atoms gets a C2 double prime. So again, a single prime indicates that the axis passes through several atoms of the molecule. A double prime indicates that it passes between the atoms. The next symmetry element that we want to look at is the mirror plane, and we said that the mirror plane is represented by a sigma. And it is a reflection. So if a reflection is an operation that reflects the object through the plane as though the plane were a mirror. So we typically use whole lines to show rotation axes, and we typically use dotted lines to show mirror planes. So if I reflect along this line, and I have the asterisk here to indicate this part of the molecule, when I reflect over the line, it goes the same distance to the line as it comes out the other side. So this asterisk moves directly across from the mirror plane. So this is an equivalent configuration, thus the molecule has a reflection plane. But actually it has multiple mirror planes, including the plane of the paper. So there is a mirror plane here, there's a mirror plane that goes through each of the carbon atoms, so that are opposite of each other, and there's one that goes in between the bonds. And there's also the mirror plane that is the plane of the paper, or the plane of the computer screen. Now if we take our picture of Frank and Kenny that we looked at when we used the identity operation and nothing happened, if I were to do a reflection, and I'll put the plane right through there, and I reflected it Notice that this doesn't produce an equivalent configuration because the cat's looking at the opposite direction. So this is not an equivalent configuration, and thus Franken-Kitty does not have a reflection plane. So we're looking at that square planar complex again that has D4H symmetry. Mirror planes that are parallel to the principal axis are termed vertical mirror planes. So remember that C4 axis that's coming out of the plane, that's our principal rotation axis. The mirror plane that contains that rotation axis, so this orange one right here, this is a vertical mirror plane because it contains the principal rotation axis. Now, the mirror plane here that passes through, that passes in between the molecules, this is a dihedral mirror plane. So mirror planes that contain the principal rotation axis and bisect the angles formed between the adjacent C2 axes are termed dihedral mirror planes. So this would be an example of a sigma D because it's in between the C2 prime and another C2 prime rotation axis. Now, mirror planes that are perpendicular to the principal axis are horizontal mirror planes. So remember, we have the principal rotation axis that's coming out of the plane of paper, but perpendicular to that is the plane of the paper, and that plane of the paper bisects our molecule, and so this is our horizontal mirror plane. And again, just to re-emphasize, the principal axis, that's the rotation axis with the highest value of n. So here it is a C4 axis. So our next operation that we want to look at is the improper rotation axis, so the SNM. And the improper rotation axis is really a combination of two symmetry operations. It is the proper rotation followed by a horizontal reflection. Now in S1, so S1, 1 means to rotate by 360 degrees. So if you rotate by 360 degrees, you return to its original configuration, but then if you do a perpendicular reflection, the only thing that's left is a horizontal reflection. So an S1 is equivalent to a sigma horizontal. So if somebody asks for the improper rotation axis for a molecule and it has a sigma h, we don't bother listing the S1 because the sigma h is just a special case of the S1. But here's an example of an S6. So we're looking at staggered ethane. So the first thing we do is the C6. So we rotate the axis by 60 degrees. So the carbon-carbon bond here, this is going to be our rotation axis. So we rotate it by 60 degrees. So this comes out forward, so it goes from the plane of the paper, starts coming out, and this then was coming out at us, now goes to the plane of the paper, and we rotated everything by 60 degrees. Now notice that the in-between step here doesn't produce an equivalent configuration, so I can't overlay these, they don't look exactly the same. But once I do the horizontal reflection, so we remember we use this as our axes, we want the perpendicular reflection through here. So as we reflect this down, so notice that this comes down, so it appears here. This molecule comes down here, and this one that was in the plane of paper goes up. So we just did a horizontal reflection. So the in-between picture, as we do the improper rotation, doesn't produce an equivalent configuration, but going from the beginning picture and doing the S6 as a total, we get an equivalent configuration. Now the last symmetry operation that we'll look at is a inversion center. So the inversion center is really a special case as well. It's the S2. So you rotate by 180 degrees and then do a horizontal reflection. So with this molecule here, you rotate by 180 degrees, so it'd be below the plane of the paper, then I'll reflect up. And so this is how we invert. Now, another way of thinking about an inversion center is finding the exact center of the molecule or the object that you're looking at. And from whatever point outside of that inversion center, so let's say I'm here on the molecule and there's an inversion center here, I make a straight line to that inversion center. And if I continue along that path and go on the other side of the inversion center and go the exact same distance from here to here that I did from here to here, that's also an inversion. So everything gets kind of inverted, it becomes inside out. So this octahedral complex that has the exact same ligands at all the same points has an inversion center. So if I invert this molecule, what was at the 1 goes to the 6 goes to the 1, the 2 goes to the 4 goes to the 2, the 3 goes to the 5, and the 5 goes to the 3. So notice how everything kind of switches places as it passes through the center and comes out on the opposite sides. So to me, that's an easier way of thinking about an inversion center rather than thinking about it as an S2. But also too, if you did an S2, so this 2 here rotates all the way to the 4, and then you do the reflection through this plane, it stays where it is, so that it produces the exact same thing. So I just want to discuss equivalent operations just a little bit more. And we're going to first look at improper rotation axis where n is odd or even. So I'm using my example of a square again, this blue square. And just to kind of keep track of how I move things, I'm putting a little orientation here. So that's not really on the object, I've just kind of secretly marked this triangle. And if I have a positive side, that means it's on the top of my triangle. And if I have a negative side, it's hidden on the back side of the triangle. So if I do an S3, remember I rotate by 120 degrees because I rotate a third of the way through a circle. So the positive comes to here. But then I have to do a horizontal reflection, so a perpendicular reflection. So what was at the top goes to the back. So this is an example of an S3. Now if I repeat the S3 again, remember I go from here to the back, then here, and I reflect, come to the top. So the S3-2, so doing the S3 twice, is the same as if I did a C3-2. Because if I hide this here and I'm not looking, and I don't look at it, and I'm just looking from here to here, it looks like I rotated it once and then twice, and it's still on the top, so it looks like the same as a C3-2. So the S3-2 and the C3-2 are equivalent. Now if I do another S3, the S3-3 is going to be equivalent with a sigma H. Because looking from here to here, it looks like I didn't move it at all. I just reflected it through the plane of the paper. So what was at the top went to the back. Now if I do another S3, and again, here I've done an S3 6 times. And once I do that, I get back to the original configuration. So the S3-6 is equivalent to the E, or the identity operation. So here we've looked at the improper rotation axis for an odd value, so the n value is odd. Now I want to look at what happens when we look at an improper rotation when the n value is even. So with this molecule, I have a rotation axis that comes out of the plane of the paper that's in the center here, and that is a C4. So we're going to do an S4 operation, so that improper rotation, the way I've marked my object at the top left here on the top, goes to the top right, but go to the back. And then it goes to the bottom right to the top. And in this case, the S4-2 is equivalent to the C2-1. So notice if I look from here to here, it looks like I just rotated it by 180 degrees. So I do an S4 again, and then another S4, and notice that the S4-4 reduces down to the identity. So having an even number operation for the improper rotation axis for the n value, and doing that operation the same number of times gets us to the identity. But for an odd number, so looking up here for the S3, we have to do it, the operation, that m value, twice the n value to get back to the identity. Now, as we start looking at molecules, we will classify them by their symmetry. So we identify molecules by their point group. So here is our point group flowchart. This allows us to determine what point group to which an object belongs. And the point group defines what type of symmetry elements an object possesses. So this is going to be the flowchart that we're going to use in class, so a point group flowchart. This allows us to determine what point group to which an object belongs. The point group defines what type of symmetry elements an object possesses. And this flowchart that I've designed is arranged from highest to lowest symmetry. Now, the flowchart does not tell you all of the symmetry elements in a group. For that, you actually need a character table. So as you look through the flowchart, first of all, you need to determine the molecular geometry. So you need to draw an appropriate Lewis dot structure and determine its molecular geometry. And you first determine, then, is it linear? So if you answer yes to a question when you make these decisions, you go to the left. If it's a no, you go to the right. So if yes, does it have an inversion center? Then it will be a linear molecule. So either a D infinity H or a C infinity V. So that would be our most highly symmetric molecules. Now our next lowest symmetry, and these are still very highly symmetric, would be our icosahedral, octahedral, and tetrahedral molecules. Then we have our rotation with the perpendicular C2s. So these would be our D groups. And then we have our C groups. So these don't have perpendicular C2s. And then our lowest symmetry elements would be the CS, so this only has a mirror plane, the CI, which means it only has an inversion center, and the C1, which means it only has the identity element. So we start from here, assuming it has the highest symmetry, and then as we exclude these higher symmetry elements, we eventually move on to the lower symmetry till we find what it actually classifies as. Now there are 5 regular polyhedra. These are the highly symmetric groups. There's the cube, the dodecahedron, the icosahedron, the octahedron, and the tetrahedron. So typically we're not going to see too many of the cubes or the dodecahedrons or even the icosahedrons. Sometimes you'll see icosahedrons with like viruses. And what we're going to be encountering, we're more likely to encounter an octahedral complex or a tetrahedral type complex. So I'd like to take a look at water as an example. If you were to use the symmetry flow chart that we saw in the previous slide here, if we took water and we ask, is it linear? It's not, because it's bent. Is it highly symmetrical? It's not. It doesn't have the tetrahedral, octahedral, or icosahedral shape. So this highly symmetrical, another way of asking that question is, do you have more than one Cn where n is greater than 2? Such as, do you have C3s and C4s, or do you have C4s and C5s, or C3s and C5s? So anything where you've got Cn's where they're higher than 2 and you've got multiple of them, so like a Cn and a C5, a C5 and a C6 or something like that. Now if it's not highly symmetrical, then does it have a rotation axis? So you're looking for the principal rotation axis, so the C with the highest n value. And typically we as chemists designate that as the up direction. So that'll be our z-axis as our principal rotation axis. So then when I look at water, it does have a rotation axis. It has a C2. And my next question, do I have perpendicular C2s? I do not have perpendicular C2s, so it's not in the D group, so I have to go to the right here. And does it have a horizontal mirror plane? So a mirror plane perpendicular to that principal rotation axis. It does not. So my next question is, does it have a vertical mirror plane? And yes, it does. So this would be in the CNV. So this would be a C2V molecule. So going back, I've determined that the point group of water is C2V using the flow chart. Now going to the back of your textbook, you have things that are called character tables. And the character tables have a lot of information for you. And at the top of the character table for the C2V point group lists the symmetry operations that are in the C2V. And it lists all of the symmetry operations. So if I look at water, it has the identity. Of course, everything has the identity. It also has a C2, so the rotation axis passes through the oxygen molecule. It also has a vertical mirror plane. So you can think of the vertical mirror plane containing the x and the z axis. So if our rotation axis was a z, then maybe the x would pass through the molecules. And then the sigma v, so that would be the yx would pass through the plane. So here is the C2 axis, and this is the vertical mirror plane, so what's in the front gets reflected to the back. And in this sigma prime, so this contains the rotation axis as well, but it also contains the hydrogen atoms. So this gets reflected, this half of the sphere goes to the back half of the sphere, so it stays the same. So this would be our other mirror plane. So the C2V has the identity, a C2 rotation axis, a mirror plane, and another mirror plane. So what I'd like for you to do is to use your worksheet to find the point group and then all the symmetry elements within that group. So on your worksheet it has the point group next to the molecule, and it also has all these symmetry elements, so you can check your work as you go, but we're just basically practicing you working through the symmetry flow chart and identifying the symmetry operations, so really building up those visualization skills. Now there's a website here, the symmetry.otterbein.edu. It's really good. It was funded by the National Science Foundation. But it has a lot of good visualization tools for looking at some of these symmetry operations. But you'll probably find that building some of these molecules with your molecular modeling kits will be very beneficial.